All right. All right. So I streamed a study session last night after my stream with Mr. O, and that was AI generated notes from the security domain, questions from a practice exam. So this one, but I do after I got off the stream, I sorted through all of all the questions I missed on the exam completely, and made a new data set and generated a new through the AI, a new set of study documents. So I just want to review some of these. So I haven't even looked at these. I generated them on the AI last night, and I actually haven't had a chance to go through it. So this is the slideshow I generated with some of my notes. I want to go through that in the video, and then do the interactive audio so I can ask questions. All right, put on some music. Do I have my Pomodoro going? Sure. Well, I'll keep track of the time. Let's go through the slideshow real quick. Okay. Okay, cool. It broke it down by domain. Zero trust, automated, scaling efficiencies. And this data set is just the questions I missed, and that covers all 4 or 5 domains. Okay, this is what the hot. See, I didn't know what a hot partition was in the database. Predictive scaling, reactive step scaling. These slides are good. Okay, that's the geo proximity question I missed with Route 53. I was thinking about geolocation with AWS WAF to solve that question. I didn't even know they had a geo proximity routing available on Route 53. Let's see. Security network perimeter defense logic. Okay, security group chaining. All right. Actually, I went over that last night in the security section. Okay, trust policies. That was new. Let's see what this code looks like. Okay. Edge, add canned ACL, effect allow. See worm protection, I didn't know that. Write once, read many. Immutable worm. Okay, and there's my flow chart. Unified enterprise blueprint. Okay, that's with Fargate and containers. Okay, there you go, Dyn. All right. I like that it gives me these flow charts at the end of the spreadsheet. I crafted a prompt to get it to generate the spreadsheet, like the slideshows like this. Okay, DynamoDB hot partition. Okay, cure that with Amazon DAX. Gateway. Predictable scaling and target tracking for step scaling. Okay, when step scaling causes latency spikes. API gateway caching. Yeah, I didn't know about that. High database costs on read heavy APIs. 15-minute tokens on IAM database authentication. Okay. All right, that's good. Let's check out. I'll look at my mind maps real quick. Okay. Showing my exam concepts for test 4. And this is just the data set for questions I missed. There we go, hot partition. All right, I'm gonna handwrite all of these. I'm gonna handwrite out all of these mind map nodes. I highly recommend mind maps. It's a lot of information in these exams and stuff like that, and the mind maps just help consolidate things visually as well. Okay, that's for database. What were the networking things? I'm just saying, I'll check security and governance. Hybrid connectivity, up. Site-to-site VPN, Direct Connect, of course. Transit gateway. Scale VPN with ECMP. Let's see. Global traffic management. Route 53, geo proximity. There we go. Route 53, TTL, DNS caching duration. Let's check out load balancing. SNI, yup, I didn't know that. API gateway caching, reduce backend load. Okay. Let's check security real fast. What came up new in IAM? Role trust policies, which are resource-based. What's encryption? Glacier and KMS. VPC security. Okay. All right, that's good. All right, let's check my video. There we go. Let's see the video tutorial we put together for me.
Welcome. In today's session, we're cracking open the AWS Architect's playbook. We're going to move past just knowing what the services are and really dig into the tough design decisions you have to make when it counts. You know, the choices that separate a pretty good architecture from a truly great one. Think about it. AWS gives us this incredible, massive toolbox. But with hundreds of services, the most powerful choice isn't always the most obvious one. A great architect understands the trade-offs, the hidden constraints, and those little gotchas that make all the difference. It all comes down to the why. So here's our game plan. We'll kick things off with plays to squeeze every last drop of performance out of your system. Then we'll switch gears to architecting for the bottom line. After that, we'll dive into security and resilience, and we'll wrap it all up with a master checklist you can take with you. All right, let's get into it. Section 1, high performance plays. This is for when latency is the enemy and speed is absolutely everything. Okay, here's a scenario I bet some of you have seen. You've got a serverless app hitting DynamoDB, but one single partition key is just getting hammered with reads. It's creating a hot partition, a nasty bottleneck. You've already thrown more read capacity at the table, but it's still slow. So what's the play?
Now, two common answers here are actually traps. First, you could bring in Elasticache. It's a powerful cache for sure, but it means a ton of refactoring. Suddenly, your Lambda function
So yeah, I think I picked Elasticache or something cache related.
need all this new logic to check the cache, populate it, and invalidate it. That's a heavy lift. The other trap, global tables. They're awesome for multi-region setups, but they don't fix the problem. They just replicate your hot partition all over the world.
And that brings us to the real architect's play, DynamoDB Accelerator, or DAX. It's this fully managed in-memory cache that just sits right in front of DynamoDB. And here's the magic part, it's completely transparent to your application. Your code doesn't change one bit. DAX just intercepts those reads for the hotkeys and serves them up from its own cache in microseconds. Problem solved with zero refactoring.
So we've got our app running super fast. Now let's pivot to that other critical pillar, cost. Because let's be real, a solution that's blazing fast but breaks the bank isn't really a solution, is it? All right, picture this. You've got a really popular API backed by an Aurora database. It's mostly just serving up reads, but all that traffic is making your database bill skyrocket. But here's the key constraint. The business says it's totally fine if users see data that's up to a day old. So how do you slash costs and speed things up? The knee-jerk reaction for a lot of people is to just add more Aurora read replicas. And yeah, that will make it faster. But what was the main goal? To reduce cost.
Yeah, I think I picked the read replicas.
Adding more database instances does the exact opposite. It just makes your bill even bigger. And something like EC2 user data, it's not even in the same ballpark. That's for setting up instances, not caching API calls. The truly elegant solution is to solve this problem before it even hits the database. The architect's play is to enable caching right there on the API gateway. With just a simple configuration, a flip of a switch really, and a time-to-live setting, API Gateway starts caching responses. Now all those identical requests hit the cache and never even bother your expensive database. It's a huge win-win. Costs plummet, and your users get a much faster response.
Let's move on to our third section, security. Because in a truly well-architected system, security isn't some feature you bolt on at the end, it's woven into the fabric of the design from the very beginning.
Okay, here's a fundamental security pattern. You have an application load balancer in one subnet, and it's sending traffic to your EC2 instances in another subnet. How do you configure the security group on those EC2 instances to only accept traffic from that specific load balancer and absolutely nothing else? Now, the common pitfall here is to just grab the CIDR range of the load balancer subnet and add that to the EC2 security group. I see it all the time. And while it technically works, it's a security risk. Why? Because it means any other resource you happen to launch in that subnet can now also reach your instances. That completely breaks the principle of least privilege. The real architect's play, the most secure way to do this, is to reference the security group ID itself. So, in the inbound rules for your EC2 instances, you set the source not as an IP range, but as the unique security group ID of your application load balancer. This creates this awesome, dynamic, and stateful link. AWS manages all the IPs under the hood, and it guarantees that only traffic from a resource inside that specific ALB security group can get through. You know, that idea of creating these direct, manageable links leads us perfectly into our next section, building resilient and decoupled systems. We're talking about architectures that are built to last, that can handle failures, scale gracefully, and evolve over time. So here's a very modern enterprise challenge. You need a central hub to process events asynchronously. But these events are flying in from everywhere, your own internal microservices, third-party SaaS apps like Salesforce or Stripe, and even partner applications. You need one service that can handle all of it.
So what are your options? Well, SQS and SNS are fantastic for decoupling your own internal stuff, but the moment a SaaS provider needs to send you an event, they can't. There's no native way for them to plug in. You'd be stuck writing and maintaining a bunch of custom glue code. And while you could use Lambda, it's really a target for events, not the event bus itself. Trying to make it the central router is just asking for a lot of complex custom code and management headaches. This is exactly the problem that Amazon Event Bridge was built to solve. It's a serverless event bus that acts as the central nervous system for your entire event-driven architecture. It has native, out-of-the-box support for AWS services, your own custom apps, and a massive list of third-party SaaS partners. It just works. You can route events with simple rules instead of writing a bunch of complex code. Okay, we've gone through specific plays for performance, cost, security, and resilience. Now let's pull it all together into a mental framework, a checklist you can use for pretty much any architectural challenge you face. So let's walk through this. First, always identify the primary driver. What are you really solving for? Is it cost? Is it performance? Step 2, what are your constraints? Remember how minimal refactoring was key for our DAX play? That's a constraint. Third, always evaluate caching layers. They are so often the most efficient fix. Fourth, think about connectivity. Is this a hybrid cloud thing? Is it global? And finally, prioritize automation. How can you codify this solution so it's repeatable and reliable every single time? Ultimately, being a great architect isn't about memorizing every service. It's about being a great investigator. It's about learning how to ask the right questions to uncover the real drivers and the real constraints of a project. The services are just the tools. Your true value is in the decisions you make. Thanks for joining me.
All right, cool. All right. That's a little nice summary joint for me to keep reviewing. All right, let's go to my audio. Let's go through audio. Let's take a quick break. We're 20 minutes in. right, let's see. All right, I'm in interactive mode for audio. Let's let's see how long. Let's see how long they generated this. All right, this is all right. So this is the culmination of the data set. When they summed it up as what decision logic for enterprise AWS architecture. All right, let's go. Let's see what we talk about.
Imagine waking up to an AWS billing alert where just, a single quietly underutilized hard drive just ate 90% of your quarterly infrastructure budget.
Oh man, yeah, that is a nightmare.
Right. Or pushing a routine DNS update that you think is perfectly configured only to watch it quietly send millions of your European users into a digital black hole for like 48 hours.
It happens way more often than people want to admit.
So today we aren't just talking about basic cloud architecture. We are mapping the enterprise minefield.
Exactly, because it's a landscape defined by just incredibly strict constraints. I mean, when you operate at a massive scale, the traditional methods of diagnosing a problem, they just completely fall apart.
You just have too many moving pieces.
Yeah, you had applications failing, latency spiking, and cost spiraling. And there is rarely a single flashing red light telling you exactly what broke. You're just navigating these diagnostic muddy waters, really.
And that is exactly why we are doing this deep dive, because if you are listening to this, you are the enterprise pro. You're the architect tasked with taking these massive, nebulous requirements, scalability, high availability, absolute cost optimization, and forging them into concrete, resilient AWS solutions.
Right. And our mission today is to construct the ultimate mental flowchart for you.
The ultimate flowchart. I love that.
Yeah. We are taking a massive stack of real-world architectural scenarios, specific edge cases, and the misconfigurations that trigger those 3 a.m. pager alerts, and we're extracting the precise underlying decision-making logic.
We aren't just going to list off a table of contents or tell you what AWS service to buy.
No, absolutely not. We're going to unpack the mechanics of why certain architectures bend under pressure while others completely break.
So we are building a best practices table and a pitfalls flowchart right in your mind, tracking the journey of a network request from the global edge through your compute and event decoupling layers down to the database storage, and finally wrapping it all in infrastructure as code.
Sounds like a solid plan. Where do we start?
Let's start right at the front door, the edge of the network. So we have a scenario where an enterprise is doing everything right on paper. They are migrating from a clunky legacy monolith to a new microservices architecture. They go into Amazon Route 53, they update their simple DNS record to point away from the old application load balancer and over to the new one.
Makes sense so far.
Right, so they hit save, Route 53 registers the change. But out in the real world, it's an absolute disaster. The users are still hitting the old load balancer. The traffic just isn't shifting at all.
Yeah, so the immediate instinct for most engineers in this situation is to assume they made a syntax error.
Oh, for sure. You'd be scrambling.
Right, they start frantically checking for a misconfigured CNAME or a broken alias record. But in this scenario, the configuration of the record itself is actually flawless.
Wait, really? Flawless?
Yeah, the invisible pitfall here is time, specifically the time to live, or TTL, value attached to that DNS record.
Oh, the TTL. So it's kind of like filing a change of address with the post office, but your friends and family are still mailing packages to your old house because they haven't bothered to check the new directory yet.
That is a perfect analogy. They just memorized your old address from a year ago, and that is precisely the mechanism at play on the internet.
Because Route 53 does...
Whoa, did someone just break the fourth wall? Let's hear it.
Hey, what's the importance of the time to live record, the TTL?
But that is a great question.
And it hits right at the core of this whole problem.
Okay, let's unpack this. The importance of the time to live, or TTL, is that it directly dictates the agility of your infrastructure.
Exactly. It's the maximum amount of time in seconds that you allow third-party internet services to cache your domain's IP address.
So if you set it really high, like we mentioned, 2 days.
You're forcing everyone to rely on outdated information for up to 48 hours, even if you just changed your backend server 3 minutes ago.
And that's exactly why our scenario here failed.
The short answer to the importance is, the TTL determines how fast you can respond to change. If you have a high TTL, you are slow to change.
If you have a low TTL, you are highly agile, which is what we need during a migration. Yep, go on.
And where do you set the TTL, in Route 53 or in the like application load balancer or something like that? Where are you configuring it?
That is a great fundamental question.
Yeah, that is a fantastic question.
You don't set the TTL on the load balancer itself.
Right, the load balancer is just the target.
The TTL is an attribute of the DNS record itself.
And since we're using AWS, that's done inside Route 53.
Exactly. When you go into Route 53 and create an A record or a CNAME record, one of the fields you configure is that time to live value.
So if we set it really high, like we mentioned, 2 days.
You're forcing everyone to rely on outdated information for up to 48 hours, even if you just changed your backend server 3 minutes ago.
And that's exactly why our migration scenario failed.
That high TTL determined how fast we could respond to change.
We need during a migration, which is what we were talking about.
Precisely. And that's what makes the TTL the expiration date we stamp on the cache.
So the short answer is Route 53, not the load balancer.
You've got it. The TTL is the amount of time measured in seconds that you are instructing those third-party resolvers to hold on to that IP address before they are allowed to ask Route 53 for an update.
Ah, I see the trap now.
Yeah, if your legacy architecture had a TTL set to 2 days, which is 172,800 seconds, those ISP resolvers are going to blindly route your users to the old application load balancer for up to 48 hours.
Completely ignoring the fact that you updated Route 53 3 minutes ago. Wow. Okay, so knowing how the caching mechanism works, what does the actual deployment flowchart look like?
Well, you have to manipulate the TTL proactively.
So if I'm migrating this monolith next Tuesday, how do I prevent the 48-hour black hole?
Long before you migrate, you go into Route 53 and drop the TTL of their active domain to something very short, like 300 seconds or 5 minutes.
But dropping the TTL doesn't immediately force the ISPs to flush their cache, right?
No, it definitely doesn't.
Right, because if an ISP grabbed the record yesterday when it was still set to 2 days, they are going to hold it for the remainder of that 2-day window, regardless of what you changed it to today.
And that right there is the crucial constraint. You must lower the TTL to 300 seconds, and then you literally just wait.
You just wait for the old one to expire globally.
Exactly. If your old TTL is 48 hours, you make the change, and then you sit on your hands for 48 hours. Only after that window closes can you guarantee that every revolver on the planet has come back, checked Route 53, and received the new 5-minute instruction.
And then when migration day hits, you update the record to point to the new load balancer.
Yep.
And because every ISP in the world is now operating on a 5-minute cache limit, thanks to that new TTL, the traffic shifts almost immediately.
Precisely. You verify the microservices are handling the load, you confirm the migration is a success, and then, and this is key, you immediately increase the TTL back to a higher value.
Wait, why raise it back up? If a 5-minute PTL gives us that kind of ultimate agility, why not just leave it at 300 seconds forever?
Because agility costs money, and it costs performance.
How so?
Every time an ISP resolver's cache expires, it has to traverse the internet, hit Route 53, ask for the IP, and wait for the response. That adds a fraction of latency to the user's initial request.
Ah, that makes sense.
Furthermore, AWS actually charges you for every single one of those DNS queries. So by leaving the TTL at 5 minutes, you are forcing millions of unnecessary queries every single hour.
Which just drives up your Route 53 bill and slightly degrades the user experience.
Exactly. You optimize for agility during a migration, but you absolutely must optimize for cost and performance during steady state operation.
That makes perfect sense. So we've solved the caching issue, and our users are actually reaching our load balancers. But what happens when the load balancers in one specific region are getting overrun?
Let's hear the scenario.
Let's say we have a social media company. They are running a localized marketing campaign in Paris, and the Paris servers can handle a massive surge. They want to dynamically alter the size of the geographic area that routes to those specific servers.
Okay, I see where this is going.
My first instinct here is standard geolocation routing. If I want users in Europe to hit my European servers, I use geolocation. Why does that fail here?
Well, geolocation routing is completely static and strictly bound by political borders.
Political borders.
Yeah, you configure it to say all traffic originating from the country of France or the continent of Europe goes to this specific endpoint.
Right.
It is an excellent tool for localizing language content or maybe restricting media distribution rights, but it does not allow you to dynamically grow or shrink a catchment area.
So if you want to absorb traffic from neighboring regions into your Paris servers, standard geolocation hits a rigid wall.
Exactly. The architectural decision here must pivot to geoproximity routing.
Geoproximity. How does the routing math differ mechanically from geolocation?
Geoproximity ignores political borders entirely. It routes traffic based on the physical geographic distance between your users and your AWS resources.
Oh, physical distance.
Right. It essentially draws radial boundaries around your server regions. But the defining feature, the tool that actually solves this scenario, is a variable called the bias.
The bias.
Yes, it's a numerical value you assign to an endpoint, ranging from a +1 to 99, or a -1 to 99.
So it's essentially a geographic slider.
That's a great way to think of it.
If I apply a positive bias to my Paris region, I'm artificially inflating its perceived size. Route 53's algorithm looks at Paris, sees the positive bias, and essentially expands its radio boundary.
Exactly. Pulling in traffic from users in Germany or Spain who would normally be routed to Frankfurt or London.
You are manipulating the routing algorithm in real time.
You've got it. Oh, back to our listener. What's up?
Hey, so what are the best use cases for using geoproximity with Route 53?
That is a fantastic question.
It gets to the heart of why it exists.
If you think about it, the core use case is dynamic traffic shaping.
The ability to dynamically alter the size of the geographic area,
Exactly. We already talked about the Paris marketing campaign.
where you need to absorb traffic from a neighboring region.
That's case number 1. Intentional load shifting.
The geographic slider idea,
Yes, you can apply a positive bias to pull in traffic from farther.
bias to push traffic away.
The second major use case is for disaster recovery or brownouts.
Failure scenarios.
If you detect that one region is starting to fail or degrade, you can apply a strong negative bias.
That artificially shrinks the failing region's reach.
Precisely. It immediately forces users on the edge to route to the next closest healthy region.
Shedding LERD and improving resilience.
The alternative is waiting for latency or health checks to fail.
This gives you a proactive dial.
It's about being able to manipulate the routing algorithm in real time.
You've got it. If the Paris campaign is wildly successful and you've pre-scaled your compute there.
You just crank up the positive bias to vacuum up traffic from adjacent regions.
And conversely, if your Paris servers are suddenly overwhelmed and facing a brownout,
You apply that negative bias we talked about.
yes, Route 53 artificially shrinks the Paris catchment area.
Shedding load by... Oh, yeah. Go on.
And by adjusting the bias, it basically automates the proximity shifting.
That is a perfect summation of the concept.
Okay, let's unhack this. The automation here is key.
Yes. The geoproximity routing policy, coupled with that bias value, does the hard work
It automatically recalculates the optimal route.
based on the physical distance and the specific bias you apply.
So you're not manually updating IP tables.
No, you are simply adjusting one slider,
And Route 53 handles all the underlying BGP logic globally.
forcing users on the periphery to route to the next closest healthy region.
That is awesome.
It gives you a granular, dial-based traffic shifting mechanism.
That rigid geolocation simply cannot provide.
Exactly. It's truly dynamic.
Okay, so we are manipulating traffic patterns globally.
But eventually, that traffic has to punch through a firewall.
And that brings us to a classic enterprise dilemma.
Let's hear it.
We have a company utilizing application load balancers, or ALBs, across multiple AWS regions.
To serve this global traffic,
However, their security compliance mandates that all traffic must route through a strict on-premises firewall.
and that firewall acquires hard-coded, whitelisted IP addresses.
The classic ALB IP problem.
Right? The architectural nightmare here is that ALBs do not have static IP addresses,
They are elastic. AWS scales them up and down.
changing their underlying IPs constantly.
This is where I see teams build just incredibly brittle solutions.
Like what?
Well, the instinct is to write a custom AWS Lambda function,
That triggers every minute, resolves the current DNS names of all the ALBs.
parses the new IP addresses, and then fires an API call to the on-premises firewall.
To update its rules dynamically, that sounds like a maintenance nightmare.
It is.
If the Lambda fails or the firewall ATI rate limits you, your traffic just drops.
It's like the bouncer at the door doesn't have the updated guest list.
Exactly. It's an operational house of cards.
The goal of enterprise architecture is to eliminate moving parts, not invent new ones.
So we need static IPs.
The flowchart path seems pretty obvious to me here.
We ditch the application load balancers and switch to network load balancers.
NLBs operate at layer 4 and they give you static elastic IPs. Problem solved.
Problem traded, not solved.
Right.
Yeah. Network load balancers provide static IPs, yes, but they're strictly region bound.
Oh, right.
If your application is deployed across 3 different global AWS regions for high availability,
You now have to provision and manage 3 separate NLBs.
which means you have multiple elastic IPs that you still have to manually manage.
Document and update in your on-premises firewall.
Exactly. And you lose all the layer 7 HTTP and HTTPS routing capabilities of the ALB.
That's a huge trade-off.
It is. The most elegant, scalable solution is AWS Global Accelerator.
Global Accelerator.
Usually we talk about that service purely in terms of performance.
Like using the AWS private backbone to bypass public internet congestion.
How does it solve the firewall IP issue?
Global Accelerator's performance benefits are significant, definitely.
But its mechanical superpower for this specific scenario is how it handles ingress.
Okay.
When you provision a global accelerator, AWS provides you with exactly 2 static Anycast IP addresses.
These two IPs become the fixed global entry point for your application.
Regardless of how many regions you operate in.
Wait, unpack Anycast for me.
How can 2 IP addresses represent servers in both Tokyo and Virginia simultaneously?
It's pretty fascinating. With standard unicast IP addressing, one IP points to one specific server.
Anycast is a network routing methodology where the exact same IP address is advertised by multiple edge locations.
Simultaneously across the globe using BGP, right?
Yep, using the Border Gateway Protocol.
So when a user in Tokyo requests that IP, the internet's routing infrastructure naturally delivers the packet to the geographically closest AWS edge location.
And then what?
Once the packet hits that edge location, Global Accelerator takes over.
And routes the traffic over the dedicated AWS backbone to the optimal regional ALB.
So from the perspective of that rigid on-premises firewall, the entire multi-region AWS infrastructure collapses down into exactly 2 unchanging numbers.
Precisely. You take those 2 static Anycast IPs, you whitelist them in your firewall exactly once.
And you literally never touch the firewall configuration again. That is incredible.
Yeah, you can add new AWS regions, you can scale your ALBs massively.
You can completely tear... Oh yeah, let's hear it.
So by adding those 2 Anycast IPs via Global Accelerator, you can basically broadcast content or ingress or egress traffic globally to different edge locations.
That is a great summary of the function.
Okay, let's unpack this. You're talking about ingress and egress.
The static Anycast IPs solve the ingress problem, which is traffic coming in.
They become the single point of entry for your global users.
Once the traffic is inside the AWS network, Global Accelerator manages the egress, or the delivery of the content.
Over the optimized AWS private network backbone.
Exactly. It routes that traffic to the nearest regional endpoint.
Which gives you the performance boost we talked about earlier.
But the core benefit we focused on was collapsing that security perimeter.
That's right, because those 2 front door IP addresses will never change.
It strips the complexity entirely out of your firewall security.
That is an incredibly powerful mechanism for security compliance.
So we've successfully bypassed the firewall headaches entirely.
Now let's talk about the physical connections to an on-premises data center.
Sure. We have a scenario where an enterprise requires a dedicated private connection to AWS.
So they provision AWS Direct Connect as their primary line.
But they need a highly available failover backup connection.
And the prompt specifies they are perfectly willing to use the public internet for this backup.
Provided, of course, the traffic is heavily encrypted.
Okay, the decision tree here is fundamentally about calculating risk and varying your redundancy strategy.
Varying it, yes, if you rely entirely on Direct Connect for both primary and backup.
You introduce a specific vulnerability, physical infrastructure overlap.
Oh, meaning the 2 fiber lines literally run next to each other.
Exactly, if both Direct Connect lines terminate at the same physical facility.
A single construction backhoe cutting through a fiber conduit will sever your primary and your backup simultaneously.
It's the illusion of redundancy because they are in the exact same trench.
Exactly, because the enterprise is willing to leverage the public internet.
The mathematically optimal choice for true varied redundancy is an AWS site-to-site VPN.
Which uses IPsec.
Yes, it uses IPsec to negotiate a heavily encrypted tunnel straight over the public internet.
So if the physical fiber line is cut, the internet traffic routes dynamically around the failure.
Completely bypassing the localized physical failure of the Direct Connect line.
Okay, varied redundancy achieved. But the scenario introduces a severe bottleneck problem.
During a failover event, VPN traffic surges and the users experience crushing latency and slow throughput.
How do we architect around that VPN throughput limitation?
Because a single AWS VPN tunnel has a hard physical limitation, correct?
Yes, it absolutely does. A standard AWS site-to-site VPN tunnel maxes out at a hard limit of 1.25 gigabits per second of throughput.
Wow, that's it.
That's it. It does not matter how much bandwidth your corporate ISP provides you.
The AWS VPN endpoint will bottleneck all your traffic at 1.25 GBPs.
If your failover traffic demands 4 GPPs, a single tunnel will literally just collapse under the load.
So we can't just pay AWS to widen that single pipe. How do we scale it?
You don't widen the pipe, you build a multi-lane highway, so to speak.
I like that.
The architectural solution points directly to AWS Transit Gateway.
Transit Gateway acts as a highly scalable cloud router for your network.
But the critical mechanical feature we need here is its
Okay. I'm information overloading right now. Let's take a little break. All right, we're back. These deep dives, man, the information is dense. Uh, it's almost white paper level. If we have to take a break, let some of it sink in. All right, we're gonna go like another 10 minutes, and that'll be my study session for at least this part of the day. Let's get back to it.
port for equal cost multipath routing, or ECMP.
Equal cost multipath. Break down the packet level mechanics for me, please.
How does ECMP manage to bypass that hard 1.25 GBPs limit?
Well, ECMP is a routing strategy that allows traffic to be forwarded over multiple distinct paths.
All of which have the exact same routing cost to the same destination.
Okay.
Without ECMP, if you build 4 VPN tunnels to AWS, your router will pick one primary tunnel.
It will send all traffic down that one tunnel until it maxes out at 1.25 GBPs.
It completely ignores the other 3, which is a massive waste of capacity.
So ECMP forces the router to look at all 4 tunnels as a single aggregated pool.
Yes, you establish multiple IPsec tunnels from your customer gateway hardware to your ECMP-enabled transit gateway.
When a stream of packets needs to reach AWS, the transit gateway uses a hashing algorithm
to dynamically distribute the traffic flows across all the available tunnels simultaneously.
That's brilliant. It's truly multi-line.
It is. If you bundle 4 tunnels using ECMP, Your total aggregate throughput scales to 5 GBps.
You achieve massive bandwidth over the public internet simply by adding more parallel tunnels.
So we've secured the front door, we've optimized DNS TTLs,
We've dynamically shifted traffic with geoproximity bias.
we've collapsed global firewall rules using Anycast IPs, even after that great discussion.
And we've built a massive ECMP-bonded failover network.
We've been very busy.
The traffic has successfully arrived at our AWS compute layer.
But all of that elegant networking is entirely wasted if the servers receiving the traffic melt down under the load.
Completely wasted. Managing compute scale is the crux of cloud engineering.
It is where you either achieve perfect operational elasticity or you watch your costs completely spiral out of control.
Due to over-provisioning, let's examine the forecasting matrix then.
We have a streaming media platform.
Their workloads exhibit highly predictable baseline patterns.
Massive viewership surges every weekend and every evening. Very typical.
However, because of dealing media, they also suffer from sudden, unpredictable viral spikes.
When a specific piece of content trends globally, like a sudden real-time surge.
They need a fully automated scaling architecture that handles both.
Now, if I'm looking at the basic auto-scaling tools,
Why can't I just use schedule scaling for the weekends and rely on standard step scaling to catch the viral hits?
that hybrid manual reactive approach is a massive operational trap we need to avoid.
Really? Why is that?
Let's break down why both of those basic mechanisms fail the enterprise requirement.
Schedule scaling forces you to hardcode time windows based on human assumption.
You say scale up by 50 instances every Friday at 5 p.m. Right.
But what if a major holiday falls on a Thursday, changing the pattern?
What if a massive sporting event shifts viewership by 3 hours,
Scheduled scaling is inherently rigid. It does not adapt to behavioral shifts.
requiring constant manual recalibration by your operations team? Okay, I see that.
And SCUP scale, like that's entirely automated based on metrics, right?
It is automated, but it is fundamentally reactive, which is the problem.
Reactive.
Step scaling waits for a CloudWatch alarm to trigger first.
For example, it waits until your average CPU utilization breaches 80% for 3 consecutive minutes,
Only after the alarm fires does it begin the process of requesting new EC2 instances.
which takes time to provision.
Exactly. Provisioning an instance, booting the operating system, passing health checks, it all takes time.
By the time those new servers are actually capable of serving web traffic, 5 or 6 minutes have passed.
During which your existing servers are pegging at 100% CPU.
And your users are experiencing severe latency and buffering? Yep.
Step scaling basically guarantees a period of degraded performance every time.
So what is the precise combination of tools to solve this proactively?
The optimal architecture combines predictive scaling with dynamic target tracking.
Predictive scaling, how does that feature work?
It utilizes AWS machine learning algorithms to continuously analyze up to 14 days of your historical CloudWatch metrics.
It learns your daily and weekly traffic patterns organically.
Oh, wow. So it doesn't need a human to hard code a schedule.
Nope, it doesn't need a human to tell it when the weekend starts.
Model recognizes the incoming surge and proactively provisions the necessary capacity before the evening spike occurs.
When your users log in at 5:00 p.m., the servers are already warm, healthy, and waiting for them.
That handles the predictable patterns beautifully. But what about the surprises?
But the ML model can't predict a random viral video spike at 2:00 p.m. on a Tuesday.
Exactly. And that is why you layer dynamic scaling with a target tracking policy right on top of it.
Target tracking.
Yeah, target tracking is much simpler and more aggressive than step scaling.
You define a metric, say, maintain an average CPU utilization of 60% across the fleet. Okay.
If that unpredictable viral video hits and your fleet's CPU suddenly spikes to 75%,
Target tracking immediately calculates how many instances are mathematically required to dilute that average back down to 60%.
and provisions them in.
Oh, go for it.
Hey, is the predictive scaling using machine learning, is that a native feature? And if so, native to which service?
That is a fantastic question, and you are exactly right.
That hits right on the head of what we were just talking about.
Yes, predictive scaling is a native feature.
And it is native to the Amazon EC2 auto scaling service.
So when you configure your auto scaling group,
You actually go in and configure a predictive scaling policy for it.
and that policy is what is doing the heavy lifting.
It's the mechanism that utilizes the machine learning.
It analyzes up to 2 weeks of your CloudWatch metrics.
And it creates a forecast of your future load.
So it's baked right into the service you're already using.
It's not some separate paid for ML model.
It automatically provisions that capacity in advance.
which is how it handles those predictable evening surges.
So yes, native to EC2 autoscaling.
That's why it is such an elegant solution.
Instantly. Oh, that's so smart.
Yeah, it handles the real-time deviations while predictive scaling handles the baselines.
It's the ultimate combination. Proactive ML for the knowns.
Reactive mathematical tracking for the unknowns. Exactly.
Let's shift gears from massive scale down to minimal baseline scale.
Okay.
We have a company hosting esports tournaments.
Their servers are deployed in an auto-scaling group across 3 distinct availability zones.
When a tournament concludes, the servers sit completely idle until the next event.
So they naturally want to scale down to minimize compute costs. Makes sense.
But they must maintain high availability, even at the absolute minimum.
What should the absolute minimum capacity of that auto-scaling group be set to?
Should it be 1 instance, or should we put 1 in each AZ and set the minimum to 3?
This scenario exposes how teams totally miscalculate the cost of availability.
How so?
If your requirement is strict high availability, setting your minimum capacity to 1 is an immediate architectural failure.
An EC2 instance, by definition, resides in a single availability zone, right?
If you scale down to 1 instance and that specific AZ experiences a localized power failure,
Your entire application goes offline.
but the auto-scaling group would replace it eventually, wouldn't it?
Yes, the autoscaling group will eventually notice the health check failure,
And provision a replacement in a healthy AZ.
but you will suffer hard downtime during that provisioning window.
So 1 instance is a single point of failure.
By that logic, since we are deployed across 3 AZs, shouldn't we set the minimum to 3?
1 instance guarding each zone.
That is the pitfall of conservative over-provisioning.
Setting the minimum to 3 absolutely guarantees availability.
But it fundamentally wastes capital during those long idle periods between tournaments.
So what's the optimal answer?
The mathematically optimal minimum capacity to achieve high availability without wasting money is exactly 2.
Walk me through the failure mechanics of setting it to 2.
Okay, if you set your minimum to 2, the autoscaling group's internal rebalancing algorithm will automatically distribute those instances across 2 separate availability zones.
Let's say AZA and AZB. Okay.
If AZA suffers a complete catastrophic failure, the instance in AZB is completely unaffected.
And continues to serve traffic, your application remains online. Oh, I see.
And then the ASG recognizes that it has dropped below its minimum required count of 2.
And because AZA is down, it immediately provisions a new replacement instance into the healthy AZC.
Wow. You maintained availability, and you didn't pay for a useless third instance during the idle period.
That's the beauty of it. That is incredibly precise logic.
And how do we optimize?
So you
Yeah,
so using that minimum required EC2 logic, does that correlate to the 2 is 1 and 1 is none logic?
That is a phenomenal way to phrase it.
Yeah, that classic industry mantra.
2 is 1 and 1 is none.
It absolutely correlates to this specific EC2 logic.
It means that if you only have 1 of something,
You essentially have 0 reliability.
because that one thing is a single point of failure.
If it goes down, your whole system fails.
So in this case, 1 instance means none of your availability guarantee holds.
And 2 instances spread across 2 AZs means 1 redundant system.
Because if 1 instance fails, the other keeps serving.
The ASG replaces the failed instance.
So we have that true high availability.
It is the foundation of resilient design.
We optimize the billing structure for those 2 minimum instances.
Because those 2 instances represent your absolute baseline floor.
You know, with 100% certainty that they will be running 24 hours a day, 365 days a year.
Right.
You should never pay the standard on-demand hourly rate for permanent baseline compute,
The flowchart mandates that you purchase reserved instances or RIs,
specifically for that baseline footprint,
which gives you a massive discount.
a huge discount by committing to a 1 or 3 year term,
RIs provide a massive billing discount.
often up to 70% compared to on-demand pricing.
You rely on on-demand pricing for your volatile peak scaling.
But you heavily discount your minimum floor.
Okay, so we've optimized our scaling policies beautifully.
But let's talk about the speed of those actual instances booting up.
Yeah, boot times.
Yeah. We have a scenario where a company is utilizing AWS Elastic Beanstalk.
To deploy a massive web application.
Their auto-scaling logic is sound, but the actual deployment takes over 45 minutes.
Ouch.
When a new instance boots, it has to download gigabytes of dependencies.
Run heavy compilation scripts.
and generate static assets before it can actually pass a health check.
They need to crush that boot time down to under 2 minutes, which is a massive demand.
Yeah, when an EC2 instance boots inside an Elastic Beanstalk environment.
It typically relies on a standard foundational Amazon machine image in AMI.
Okay.
If you are forcing that fresh instance to execute a massive initialization script every single time it spins up,
You are crippling your elasticity.
your auto-scaling group might realize it needs more compute immediately.
But it is forced to wait 45 minutes for the server to actually build itself.
This is like trying to bake the bread and make the sandwich while the customer is standing at the register.
You have to prep the ingredients beforehand.
How do we mechanically split this workload in AWS to speed it up?
The architectural decision forces us to bifurcate the initialization process.
Into two distinct prices, static baking and dynamic contextualization.
Okay, so what's static baking?
Everything that is heavy and unchanging.
The base operating system, the hardened security patches.
The massive software dependencies and the static application code.
Must be baked into a custom or golden AMI.
You build this image in a CI/CD pipeline long before the application ever needs to scale.
Exactly.
So when the auto-scaling group requests a new instance, it uses that golden AMI.
The heavy lifting is completely bypassed.
Because the dependencies are already physically written to the EBS volume attached to the image.
You've got it. The instance boots in seconds rather than minutes.
However, you cannot bake literally everything into an AMI.
Right, because you still have highly dynamic variables that change based on the specific environment.
Like fetching temporary database credentials from Secrets Manager.
Or passing in environment-specific configuration flags that are sensitive.
Exactly. If you bake a database password into an AMI, you've created a massive security vulnerability.
So how do we inject those dynamic variables at boot time without slowing down the deployment?
You handle those lightweight dynamic requirements using Amazon EC2 user data.
User data.
Yeah, user data allows you to pass a small bash script or cloud init directive to the instance.
That executes automatically during the final stages of the boot process.
So it's super fast.
Very fast. By combining a golden AMI to handle 99% of the heavy static installation,
And utilizing EC2 user data to rapidly inject the 1% of dynamic configuration at runtime,
you seamlessly drop a 45-minute deployment bottleneck down to under 2 minutes.
that is a massive operational win for elasticity.
Let's push further into the compute layer.
We have a company migrating.
Oh, go for it.
Hey, so what's the relationship between the using the golden AMI and the user data? What's the configuration with that again? For rapid boot time?
That is a fantastic question, and it helps clarify the separation of concerns.
Okay, let's unpack this. The relationship is one of necessity and security.
The golden AMI handles all the heavy static stuff.
Things that take a long time to install.
Exactly. All the software installation, operating system patches, and the application code base.
You bake that in beforehand to make the boot time fast.
User data handles the light, dynamic stuff,
It's the secure injection point for things that change per environment.
like API keys, environment variables, or temporary secrets.
We separate them because baking sensitive credentials into the AMI is a major security flaw.
And trying to install everything via user data makes your boot time painfully slow.
So the AMI solves speed for static components.
And user data solves security and speed for dynamic components.
It's a two-part architectural fix for that 45-minute deployment problem.
Exactly. So where were we? We were talking about compute layer challenges.
Yes, we were moving from slow deployment to serverless containers.
We have a company migrating their monolithic APIs into Docker containers.
And the primary non-negotiable requirement is that the solution must be entirely serverless.
They do not want to manage operating systems at all.
This decision tree is solved quickly by eliminating the launch type.
If the requirement is strictly serverless, you must eliminate Amazon EC2.
Even if you use a managed orchestrator, if the containers are on EC2 instances,
Your operations team is still responsible for provisioning those virtual machines.
managing the AMI patching and handling the OS security updates.
That is not serverless by any definition.
Okay, so EC2 is out.
We also eliminate big data clusters like Amazon EMR.
And machine learning endpoints like SageMaker.
Those are powerful, but are not general business microservice platforms.
So where does the flowchart route us for true serverless containers?
It leads to two primary orchestration planes, ECS or EKS,
But the critical architectural requirement is the compute launch type.
which must be AWS Fargate.
Break down the mechanics of Fargate. How does it eliminate the server management?
Fargate is a serverless compute engine explicitly built for containers.
Instead of provisioning an EC2 instance to pack multiple containers onto it,
You package your Docker image and specify the exact CPU and memory required.
Define your networking and IAM policies and hand it to Fargate.
And Fargate automatically provisions an isolated micro virtual machine just for that specific container.
AWS completely abstracts away the underlying infrastructure.
You never see the server,
You never see it. You never patch the OS.
and you only pay for the exact resources your container consumes.
Pairing ECS or EKS with Fargate is the absolute definition of serverless container orchestration.
Perfect. We have a highly scalable, serverless compute layer.
But those microservices need to communicate with each other.
If service A has to wait synchronously for service B to respond.
A sudden traffic spike will cause a cascading latency failure.
That brings us to data tier decoupling.
Asynchronous decoupling is the absolute secret to resilient scale.
Let's examine a decoupling scenario.
We have a third-party SaaS application, a CRM platform.
This
Can you explain asynchronous decoupling to me in the simplest way possible?
That is a wonderful question.
And it is vital to understanding resilient architecture.
Okay, let's unpack this. In the simplest terms, synchronous means you wait.
If service A calls service B synchronously, service A literally pauses.
It stops all its work until service B returns an answer.
If service B takes 10 seconds to respond, service A is blocked for 10 seconds.
Now imagine 100,000 users hit service A at once.
They all get blocked, waiting for the slow service B.
That's a cascading latency failure.
Asynchronous, on the other hand, means you don't wait.
Service A sends a message and immediately goes back to work.
It says, here's the data, process it when you can.
It doesn't care when the other service is done,
This is usually done with a message queue or an event bus.
like we're about to talk about with EventBridge.
It absorbs the traffic spike and processes it at its own pace.
The beauty of asynchronous is that service A and service B don't rely on each other for time.
That is the ultimate secret to resilient scale.
Asynchronous decoupling.
So now back to our scenario. We have that third-party CRM platform.
This external CRM needs to feed real-time customer updates to our internal AWS applications.
We need to decouple them asynchronously to prevent failure.
Our common tools like SQS or SNS are the wrong choice strictly because of the origin of the data.
As we've discussed, SQS and SNS are for decoupling internal microservices that you control.
But this is a third-party SaaS app that we don't control.
They do not possess native ingestion integrations for external SaaS providers.
So forcing SQS requires custom glue code, a Lambda function, and an API gateway endpoint.
That introduces entirely unnecessary operational overhead.
The decision flow chart forces us to Amazon EventBridge.
EventBridge is an advanced serverless event bus service.
It is specifically engineered to solve this exact ingestion problem from outside AWS.
It features a mechanism called a partner event bus.
This provides direct, native integrations with dozens of third-party SaaS platforms
The SaaS application drops the event directly onto the EventBridge bus.
without any custom API gateways in between.
Exactly, and its real power lies in its routing logic.
You configure declarative rules within EventBridge that expect the JSON payload,
If the rule matches the pattern, EventBridge automatically routes it to a specific target.
like an AWS Lambda function or an SQSQ for further buffering and processing.
It acts as the ultimate low-code universal router for internal and external data.
That is incredibly elegant.
Let's look at another asynchronous data movement scenario involving massive file storage.
We have an analytics enterprise with terabytes of existing historical log files stored in an S3 bucket.
And a constant stream of new log files landing there every minute.
They need to stream all of this data backlog and real-time updates into Amazon Kinesis data streams.
As fast as possible for real-time analytics.
My instinct is still an S3 event notification triggering a Lambda function.
Why is that architectural pattern a trap, even with the goal of asynchronous movement?
Because you are taking on the burden of custom software engineering.
The Lambda function has to manually handle file parsing and retry logic for Kinesis throttling.
You also have to manage Lambda's memory limits for massive files.
And crucially, S3 event notifications only trigger on new file creations.
Wait, what about the terabytes of historical backlog?
Exactly, you need a completely separate complex script just to iterate through the backlog. It's a massive maintenance sinkhole.
So the surprising service that handles this without custom code is AWS Database Migration Service, or DMS.
Wait, how does a database migration tool solve a flat file S3 streaming problem?
That is the most common misconception.
Under the hood, DMS is a remarkably versatile, highly optimized data replication engine.
The decision matrix points to DMS because it natively supports S3 as a source endpoint.
And crucially, it supports Kinesis data streams as a native target endpoint.
So DMS can read flat files from S3 and translate them into a real-time data stream.
Without you writing a single line of custom parsing or retry code.
You configure a DMS replication instance and point it at the S3 bucket,
DMS performs a full load operation, churning through all the existing historical terabytes.
pushing it into Kinesis.
Once it's caught up on the historical data,
DMS seamlessly transitions into a changed data capture phase, or CDC.
it actively monitors the S3 bucket.
And the moment a new file lands, it streams the new records into Kinesis with minimal latency.
It natively handles the throughput scaling, error logging, and the formatting.
It is a brilliant, entirely managed solution for that problem.
That is a total paradigm shift.
And that seamless movement of data leads us perfectly into the deepest layer of our architecture.
Database and storage selection.
This is where applications usually hit their most brutal physical constraints.
We have a serverless.
All right. We're an hour in. All right, I'm in information overload. My brain is fried. But that was a good deep dive into the question set that I missed on the exam. I'm actually going to go back and read through some stuff. All right, but this is a good review. All right, we're out of here.